Basically, a gyro is a rotating wheel in an assembly, typically a gimbaled assembly, although ours aren't quite gimbaled, and I'll explain that later. The original idea came from a French physicist, Leon Foucault, and he invented that in 1852. The first patented gyro in the United States was patented by a gentleman by the name of Elmer Sperry in 1908. His gyro system was basically counter-rotating wheels in a gimbaled assembly, and once those wheels were spinning at full speed, after a period of time, they would align themselves with the spin axis of the Earth, which is true north. With a gyro that knows where true north is, you can get from point A to point B in a straight line quicker, which is very important when you're talking about a naval fleet. Something else that he was instrumental in was that there was a gentleman by the name of Pugh at Sun Oil Company, and they were drilling a lot of wells in Signal Hill, California in the early 1900s. They were putting casing down there, and they were running a magnetic-based compass system to find out the direction of these particular well bores. They knew that they were having issues with that, so they approached the Sperry Gyroscope Company and asked him if he could develop a system with a gyro that could actually measure the deviation direction of a well bore, and he ultimately did that. That happened in approximately 1929. Those systems are based on a spinning mass and a gimbaled assembly. Once they reach speed, you have to actually orient the assembly to a known direction, and then it works off the principle of inertia. From there, we've gone to smaller strap-down gyro systems that actually don't operate off the principle of inertia, but they operate off the principle of precession. Precession is when a force is applied to a spinning mass, the gyro. It reacts in a plane perpendicular to the applied force. That's very important for what we do at Gyrodata, because we're actually using the Earth's rotational velocity to find north. As the Earth rotates from west to east, the spinning mass is oriented in a vertical position parallel with the Earth's rotation. The force applied is the Earth's rotation. It reacts in a plane perpendicular and gets canted ever so slightly to the north. That's how we know where north is with the systems that we run today. The Gyrodata in the early days actually started using a gyro that was built by a company called Inkeson out of California. Those particular gyros were sold to the United States government for missile guidance technology. That was in 1980 when that happened. We needed a gyro that was small enough to go down inside something smaller than 9 5/8 casing, and also any instrument that goes down inside of a wellbore is temperatures can become extremely hot. So we needed to develop a gyro that we could actually run up to very high temperatures that were rugged. We've looked at every gyro on the market, and they just couldn't meet the specifications that we required. That's why we ultimately had to build our own system. Ultimately, we came up with a gyro that's this size. It's about the size of a penny. We've had a gyro manufacturing facility in Southern California for many years now. They've actually developed a gyro small enough that we can put it inside a 1.8-inch OD pressure housing, and we can actually mechanize these gyros so that we rotate them, which is part of our process. And to take this instrument and to be able to rotate it parallel or perpendicular, to the pressure housing was quite a feat. When we measure Earth rate of the Earth's rotational velocity, we're measuring 15.041 degrees per hour. So something else that this particular gyro was the only gyro that was really been developed specifically for the oil field to handle high temperatures, shock, and also have the accuracy that we need when we run down on wellbores to obtain the smaller ellipses of uncertainty and better wellbore placement. Magnetic instruments have been around for a long time. They've been using solid-state magnetometers, which are extremely accurate, but they're also measuring the Earth's magnetic field, which is diurnal, which means that it's constantly moving. It can also be affected by metal in the earth and different anomalies. Also, drill pipe is metal, so you have to run those assemblies in a non-magnetic collar to try to accurately measure the Earth's magnetic field without any influence from magnetized steel. With the gyro, it's not affected by typical magnetic fields, so we can run that inside of casing and make measurements after the fact. If they want to do a re-entry and cut a window in an old well to save the cost of the infrastructure that's already there, we can orient that assembly inside the casing so that they come out in the right direction. Also, the ellipses of uncertainty based on a gyro are smaller, so it gives them more confidence in where they put the wellbore geologically into formation. Initially, when we started running gyros, we did only surveys inside of casing once the well was drilled. And that was because our gyro was inside of a 2.5-inch pressure housing. As time progressed and we miniaturized the gyros themselves, we were able to put these assemblies in 1.75, 1.875 housings that hold higher pressure, and we can run them down inside of drill pipe. We can also attach a gyro, what we call GWD, or gyro while drilling, to a magnetic assembly for better accuracy, and it allows us to actually kick the well off real time with the instrument down hole. The data then gets pumped up so the directional driller can see what direction he's actually drilling the wellbore. That's very useful. Something else that we're very proud of and what we do at Gyrodata is, behind me you can see what we call our calibration stands, our master calibration stands. Every gyro that we have, when it's brand new, goes into one of these stands. It's aligned, and then it goes through a 10 temperature calibration. We know that when we build the instruments, we actually put them in a thermotron. We heat and we cool several cycles to de-stress the metals. But we know that when we elevate the gyro to a temperature going from room temperature here in the building to 150 degrees centigrade, the physical characteristics will change ever so slightly. So we actually model that over 10 different temperatures to maintain the accuracy of the gyroscope in a wellbore, no matter what the temperature is, up to 150 degrees C, static, in regular pressure housings, or we can run to 500 degrees Fahrenheit inside of a heat flask. During the 10 temperature calibration I mentioned earlier, the tool is put in a series of positions. It rotates around its tool face axis. It rotates up and down for angle or inclination, and it also rotates around azimuthally. After these calibrations are done and the gyro's been put in a lot of different positions, we actually calculate what the gyro measured at each one of those positions, compare it to the known position of the calibration stand. That way we can quantify the accuracy of the gyro tool face itself, the accelerometers for inclination, and we can also quantify the spec or the accuracy of the actual azimuth. We can do that on every instrument that leaves. When an instrument leaves with that calibration, we have a way, what we call a roll test, to verify that the calibration hasn't shifted. That's something that's very unique to Gyrodata, so we can actually quantify the surveys that we've run based on a lot of math that's been put into it, and these calibration stands that quantify the actual instrument specification. I'd like to thank you very much for your time, and I hope you found this very educational.